So this is known as an LC circuit for obvious reasons. And there's a couple different ways you can build one of these. I've built it the clunkiest way possible, but there are more elegant solutions to this. The purpose of a circuit like this will probably become somewhat obvious after we get to what it's going to do, but you've got to have some idea of what you expect to see here. If you've kind of been paying attention to a general theme of most of what I've talked about when it comes to anything in physics, is that we're generally trying to find a path to track the energy and the way energy moves from one form to another in any form when we deal with, what I feel is the realm of science and physics. That's no different here. We're going to spend a little bit of time charging the capacitor, and then when we open up that switch and close the second switch, the energy that's in the capacitor is going to be shared with the inductor. And how that happens is something that I think is somewhat interesting, but how we use this I think is more interesting. So I want to look at the math of it, but the math is outside the scope. So we're going to try something here that I think you'll find insightful. So if you'll recall, we closed switch 1 long enough so that we have the full voltage supply across the plates of the capacitor. This gives us kind of a starting point for the energy that we have in the system, as it'll be 1/2 CE squared. Right, total amount of energy that's in the system at the start of this problem. We could actually approach this problem by looking at energy when it comes to seeing with how this circuit behaves. But again, I think where I veer from something we already know, we know that we can look at the way a circuit performs by looking at Kirchhoff's laws. So that's why I thought we should probably look at Kirchhoff's laws. And that meant that we look at the voltage drop across the capacitor, the voltage drop across the inductor, and we set that equal to 0. Across the capacitor we get Q over C, and across the inductor we get L di dt. And then from here we did a substitution, and that substitution was to take what we know about current, which is dq dt, and sub it in for current in di dt, and get this monstrosity, which is written like this. And have you guys done this in calculus at all? Second derivative notation? This is not saying that you're taking and squaring the d or squaring the bottom. That's not what it says. It says specifically that you are taking the derivative of a function twice. That's what it says. So don't confuse it. The notation is cumbersome if you'd ever go on and take something that's more maybe more involved when it comes to not just physics but mathematics, they won't write this kind of stuff out. There's a shorthand notation for the way you can write derivatives that doesn't require it to be a fraction every time. The shorthand is different for different disciplines, but for something like this where we're dealing with derivatives with respect to time, it's often common to write the first derivative as merely a dot on the top of your function. So a dot on top of a q would mean first derivative with respect to time specifically. So this would be considered just a double dot. It's just a shorthand notation, and no one told me that there was a shorthand notation that existed. I figured it out 3 weeks into my first class where the professor had been using it for weeks, and I was too much of either a moron or too cowardly to say, I don't really know what he's doing, but I'm just going to copy it down word for word. But by the 6th class period, I decided I needed to ask somebody, and so I asked the person next to me, and they said, I have no idea either. So I did what was considered heathenish at the time, raised my hand, interrupted Professor Harry, and said, I have no idea what the dots mean. And he goes, why didn't you ask that 3 weeks ago? And I said, well, first college class I ever attended, physics, I am a physics major. I thought perhaps I was just too stupid and everybody else knew what I was supposed to know. And he goes, well, let me explain it. He was actually quite a nice guy. I ended up working for him years later. But at the time, yeah. So just keep in mind, even adults had their moments back when they were your age and did the same kind of stupid stuff you guys generally tend to do. So put that hand in the air when you don't understand something. Go ahead and look stupid. You might as well. Just remove all doubt. It's just faster that way. So I want to talk a little bit about what this says, but let's go ahead and do a quick substitution. So I have minus Q over C equals, I'm going to go ahead and move the one function over to the other side. So I have L times d squared q over dt squared, which is just, we wouldn't say that, we would say it's the second derivative of q with respect to time. In calculus parlance, a differential equation that has a first differential is called a first order differential equation. And a differential equation that has a second derivative would be called a second order differential equation. So this is a second order differential equation. But you don't have a tool set. We can't do splitting the derivative here. So because we can't do splitting a derivative here, we're going to need to find a different way to solve this. And I have an entire book of other ways to solve this, but this one, there might be a way to solve it that doesn't require any kind of real differential equation knowledge. I'm going to take a minute and just get the differential by itself. Now, some of you, and I hope that there's people in the room who remember this, will recall us doing this last year. So it should look familiar if you're in mechanics last year. Now, if you were in mechanics last year in AP1, we didn't do anything like what we're about to do here. But what we're going to do is actually, we're going to try and guess what the solution looks like. And that's chapter 1 in any differential equations book. After splitting a derivative is just guessing for stuff. This works only because we're dealing with a very special circumstance of this kind of function. And I will show you the very next circumstance in which it doesn't work after we get done with this one. But we're just going to guess at a solution. But if you look closely at what this says, it says that if I take the derivative of a function twice, I get back the original derivative and a constant. You guys see that? That's what it's saying. It's saying if I take the second derivative of a function about q, I will get the original function back, and I'll get a constant out front. Do you guys know any functions that give you back the original function when you take the derivative? Yeah, you should know a couple of them, right? So there's, in this case, we're going to do t, because this is about time. So yeah, we know e to the t will give you back the original function. So that's a possible contender. We could maybe try it out. Now understand, you have to build a function that might follow the rules. So for one, e to the t is a unitless quantity. So I would probably put like a q naught out front to remind me that there has to be some value that represents the charge at time 0. So when you're building a function, you have to remember the qualities of that function have to persist. And I will probably need a constant here, because remember, there's a constant out front when I take the derivative. You guys see what I'm saying? So I need something in the location where when I take the derivative, I'll get that constant. So if we take the first derivative of this function, which we just built and guessed at, we would get c times q naught e to the ct. We take the second derivative of this function. We'll get c squared times q naught e to the ct. Well, this is all q, right? The original function. So if I was to look at what we've created by guessing at a starting point, I would be able to say that this function looks like d squared q over dt squared equals c squared times q. How close is this model function to what we're trying to get? I'd argue close, as long as c was the square root of 1 over LC, right? So if I made that replacement, that would work. But it's not exact, is it? There's also a negative sign there. So I need to reproduce the function exactly. This does not reproduce the function exactly. So we might try something else. And I think, I think you know where I'm going with this, but let's fail one more time, because I always think that a couple of failures isn't a bad idea. A novice might think, well, if I put a negative sign here, that might fix my problem. And of course, it doesn't fix my problem, because in the first derivative, I do get a negative sign for sure. But in the second derivative, that negative would cancel out. And so I'm not left with a function that produces a negative sign afterwards. So this can't be our function. So we're going to guess at another function. And you guys know what the other function must be, Or at least a few of you probably have an idea of what the next function must be. What do you think we should try instead? We have a choice, right? We know that cosine or sine could both work here. Now, in both instances, by the time I make it to the second derivative, I have a persistent negative sign that will be produced. So if I take the derivative of cosine, I get minus sine. If I take derivative of sine, I get cosine. If I take the next derivative, the negative sign would persist and I'd get cosine back. And if I take the next derivative here, I'd get my minus sign and I'd get sine back. So in either case, we could probably build a function with either sine or cosine. Is there any reason or argument for one over the other? Go ahead.
The t equals 0.
The t equals 0 case is a good thing for us to consider. That at the t equals 0 case, we probably want there to be charge on the capacitor. So when I look at like the charge on the capacitor, which is what this function is about, at t equals 0, if I choose sine, that would suggest that the cosine would have, that the capacitor would have no charge on it, because sine as a function is 0 when your argument is 0. So it makes sense to use cosine, but I hate to say it, in a lot of math classes, they will force you to use sine and a phase shift to produce the appropriate starting amount. I don't want to. I just want to use cosine if you guys are okay with that, because it just seems easier to me. But sometimes you have to do whatever it is your professor tells you to do, and sine with a phase shift will produce the same results. So, but we're going to do cosine because we're not going to worry about phase shifts. Now, let's go ahead and build a function that behaves exactly like the function we have there. I'm going to start by putting a Q naught here because we still have to have whatever the charge was on the capacitor at time equals 0. And then inside here, rather than putting C, a little constant, let's go ahead and consider what that should be. Inside a cosine function, technically, the variable you're supposed to use is omega, because this is an angular frequency. But let's just go ahead and put what we think omega should be. You guys have an idea of what omega should be? Well, that was a nice mumble. Thank you. I think it's going to be 1 over the square root of LC. You see why I'm choosing square root of LC? If not, let's look at the future of what happens. When I take the first derivative, I will get 1 over the square root of LC produced from my derivative. I'll still have Q naught, and then I'll have sine of 1 over the square root of LC times t. If I take the next derivative, well, that's going to bring out another 1 over LC. I'm sorry, 1 over the root of LC. So I'll get 1 over the root of LC times 1 over the root of LC times Q naught times the cosine of 1 over the root of LC times t. Do we now see why I chose the square root of LC? Now, if you didn't like that, you could have just put omega here, done this twice, so let's just take a look at this. We're pretty close to the end here. I think we have successfully produced a function. But yeah, we could have just used omega as a placeholder the whole time. We would have ended up with an omega squared here, and we would have just equated that to 1 over LC. I was just trying to cut out that part, thinking that many of you saw what I saw. But now that you've seen it, you understand why I chose 1 over the root of LC inside there. Now, what's interesting is, without any further discussion, 1 over the root of LC has to have units of inverse seconds. It will have to work out. Now, you should do that because you know how weird the units are for the Henry and for the farad. But if you multiply a farad times a Henry and invert it and take the root, it must have units of radians per second or nothings per second. It has to work out that way. You should try it at home. It'll be fun, maybe, not really. But let's consider then that this must be the function that describes the charge on the capacitor. And its first derivative, which we have right here, must be the current that is passing through the circuit, right? It has to be. In fact, this is di dt, which would describe the voltage across the inductor over time. So if we consider what's happening in the circuit, we're going to have maximum charge, then converted to energy in the inductor, then converted back to energy in the charge in the capacitor. This is an oscillator. So this system oscillates energy between the capacitor and the inductor. And it looks like we could tune it to oscillate at the frequency we decide by choosing L and C carefully. You guys see that pretty clearly? I'm hoping, because L and C represents the angular speed. Now, this part you probably don't remember from mechanics, but this would be in radians per second, because you have to have something that's in radians if you're going to take the sine or the cosine of it. But we tend to measure things in hertz. So if I wanted to convert this to hertz, it wouldn't be too hard to do so, would it? You guys remember how to convert something from radians to not radians? Go from radians to oscillations. Standard frequency would be omega divided by 2 pi. So this would be 1 over 2 pi times the root of LC. So I couldn't get to the end of like why this might be valuable. So tomorrow we'll do this and we'll do an LRC circuit. Now we can't do the math on the LRC circuit, and you'll see why pretty quickly.